Let me introduce you to this beautiful gentleman, Aram Havarneanu. Okay, not bad. The pronunciation is not the best, but the person is great. Aram is a generalist. The common theme across his career has been applying mathematical methods to develop correct, reliable, and understandable systems. He has helped develop hardware, operating systems, security protocols, cloud infrastructure, compliers, formal specifications, and proofs of their implementation. He currently focuses on using new computer languages to facilitate the process of designing software and systems by raising the level of abstraction developers need to understand and ensuring these abstractions do not leak through formal methods. Today's talk by Aram is also about cloud computing. He's going to touch upon topics like why cloud computing is still a little bit too difficult to go on and what is the real problem with cloud. Aram, it's a pleasure having you here with us. Please give a round of applause to him, and the show is all yours.
Thank you for the introduction. So, I work on the cloud. I work on cloud systems. And in my mind, some things doesn't seem quite right. It's too difficult to work. It seems like even trivial problems involve like layers of bureaucracy and complexity. And that doesn't seem right. And if you ask other people why that would be the case, some might try to argue that perhaps it's like inherent complexity, like we're dealing with scale and the way systems scale simply require this sort of complexity. But that never sounded right for me. And in a way, we're just pushing the explanation or for what the problem is away. It's a cop-out answer. It doesn't answer what is the source of complexity. And for a long time, I didn't have an answer to this question. And I was looking for an answer, and I only started to understand this problem when I started working and studying type systems and programming languages in general. And I quickly identified that the source of what I consider to be the problem with the cloud today can be explained if we understand a little bit what the programming languages mean. And I will be talking about meaning in this talk because the problem with the cloud is very subtle. If it wouldn't be subtle, we would have solved it already. And people definitely observe that dealing with cloud is just too much complexity, and they try to build all sort of tools that will try to abstract the complexity away. But I don't think we have quite a good answer, and I think that's because we don't really grasp the fundamental nature of the problem. So the problem is subtle. So to understand a subtle problem requires quite a lot of explanation because we're dealing with things which are quite obvious, but we have to put them in the right context and relate things to each other. So we really need a fundamental grasp of what things mean. And I'm going to go pretty deep on this rabbit hole with questions like, how do we understand anything at all? What does it mean to understand? But I will start with a more simple question. Like, if I ask you what is a computer, I mean, everybody has computers, like phones. I have a computer on my wrist. Now, if I give you 10 minutes or 15 minutes to think about this problem and come up with a definition, I think that pretty much everybody will be able to come up with some relatively convoluted definition that captures the essence of what a computer is. And everybody else would be satisfied with this sort of definition. But I'm not going to give you 10 minutes. In fact, if I do this experiment, and I've done this experiment in real life, I gave 2 seconds to people to think about them. And they come with this sort of answers, which are definitely not complete, and we'll go through them, but they have something in common. And they indicate the way people think about the questions. So for example, the first question, what is a computer? A device that computes. Now, we don't like this definition because it's self-referential. So we don't like that, although it's quite interesting. Why don't we like that? We have, like in computer science, we have no problem with recursive functions and things like that. But here we do not like, and I will stress the word like because it will come back later. We don't like this sort of recursive definition. We seek a different sort of answer. But even with this very, very primitive definition, we can see that it seems that we're trying to reach for a notion of what is computer, and we understand that it has something to do with computability, and we place computability on a ladder higher up than what it is a computer. So we're not even referring, like when you try to give a definition, you're not referring to any concrete computer, but you're trying to grasp for something higher, even though you haven't defined it. A black box with input and output. Not right for reasons that we'll gonna go through, but this one is again interesting that we seem that it seems to be that it's fundamental that it doesn't matter what's in the box. It's about the observable behavior that happens outside the box. Okay, that's interesting. I want to keep that in mind. A programmable device. I mean, okay, let's assume that we understand what it means to be programmable without the computers, because we did different sort of programming before computers. I'm going to go show one example in the next slide, actually. So again, we seem to refer to the thing that the computer can do, because that seems to be more important, the fact that it's programmable, than what it actually is, which is, again, interesting. Of course, computers run instructions, and we give instructions to them. I mean, primitive programming languages are very imperative in their nature, and we give instructions to computers, like assembly languages give its instructions to the computer. Is that fundamental? Well, we need to program it some way, so perhaps it is fundamental. But as we will see in a couple of slides, this doesn't quite capture it, and it doesn't quite get to the point of it. And I'll briefly talk a little bit about the last one. Like, I actually had someone answer this to me, which I found quite interesting, because Turing machines are real computers are definitely not equivalent to Turing machines, because real computers have a finite amount of memory, so that cannot be true. Yet again, we seem to reach for some notion of computability, because we understand that that's important or meaningful to us, more so than any concrete computer. So again, we refer to something else. In our quest for understanding something, in a quest for explaining something, we refer to something else that maybe we hope we know what a Turing machine is. But as I've been doing this experiment again and again, there's one particular sort of definition that nobody ever gave to me, which is something like this: that a computer is an analog device that processes electrical signals in a very particular way. Nobody gives this sort of definition, which is quite interesting, because this is obviously more factually correct than all the previous ones, which even though we weren't very happy with them in general, they weren't complete, they sort of captured more of what the computerness of the thing than this sort of definition. Real computers are definitely analog devices, and they definitely use electricity, but it seems that it not only doesn't matter, for our understanding, we simply reject to look at this level of abstraction. And it's interesting, because it's not like we have other sort of computers, like positronic computers or whatever, which we could refer to and generalize from. No, we only have this sort of computers. But the particular configuration or creation doesn't seem to matter really at all. Understanding of computers, at least, we will look at other things, seems to be abstract always. We're always referring to some sort of abstract concept which lives inside a model in our heads, at least. Now, primitive computers use punch cards. And you'd encode the instructions on punch cards, and you feed them to the computer. And the computer would execute them. This is one of the definitions that we had earlier, a thing that executes instructions. And here we have an example of a program. I think this one is the Apollo Guidance Computer program, actually. I'm not 100% sure. But look, I didn't tell you that the name of this sort of thing with cards in it, it's called a deck of cards. But I didn't even tell you that at the beginning. I told you this is a program, and you simply accepted this explanation. Because what was interesting about the thing was that what it represented, not like it's physical construction or anything like that. We definitely understand that this is a program, which is a very abstract thing, right? But anyway, we take these punch cards and we put them in the computer, and it runs them, yes, but we have other things that use punch cards, or things that are very, very similar to punch cards. On the left, we have a musical organ. There's music encoded, they call books, book music. Encode the music onto the tape, in this case, and it plays the music. On the right, we have a device called, let me just make sure I don't mess this up. It's a programmable Jacquard loom. It was used in the textile industry. I don't know exactly what it does, but it's instructions. It's the encoding of instructions fed to a machine that would then perform the work that you wish to perform. Okay. Well, let's try to listen to the organ to see it in action. If it works. Okay, enough of that. So, I would think that everybody would agree that this is not a computer. But why isn't it, though? And in fact, not only it satisfies the definition that we feed instructions to it and it executes the instructions, it even satisfies other definitions like the black box thing. We put an input into it and music comes out. And yet, it's definitely and obviously not a computer. So what is it a computer? What is a computer then? Well, I think at least. Oops, sorry about that. Okay, hopefully that's, yeah. Right. So we expect computers to do a specific sort of thing for us that we, again, abstractly understand like computation, although we haven't defined that at all, but we will look a little bit deeper into the whole thing. But we expect computers to do something for us, which we quantify as being useful. And in fact, the first computer, this one is the ENIAC, one of the first computers, was used to do ballistic calculations for the army. So again, it was very difficult to program this computer because it required actually hardwiring all those cables in the patch panel. But let's think about it. How did it actually work? So we wanted to predict like what a ballistic missile will land or something like that. But the computer doesn't know anything about the real world or about missiles or anything. So it required us to do some sort of encoding of information. It required us to do a model, and I would stress that word, a model. And somehow, the model had to have some sort of representation that's meaningful for the computer as well. But the modeling thing is, what kind of information do we put in the ENIAC? We probably put things like the density of air, size and shape of the missile, gravitational acceleration, things like that, to look like a physics model. Do we put the color of the sky in the model? Or the color of the grass? Or some other sort of thing like that? No, we don't. But why don't we? Because it doesn't matter. But why doesn't it matter? Because we understand how the physical world works through physics, but what we do in physics, we just create models, physical models. And to do them, we need to decide what to put in the model and what to exclude for the model. And that requires understanding. So we need these three things that need to happen here. we need to model things, and they have to have a particular encoding. And the encoding is not completely arbitrary, as we will see. And when we need some sort of understanding about the system, which requires abstraction. So you cannot get rid of abstraction. There's no concrete layer underneath, there's no abstraction. And notice that these abstractions, all of them happen essentially in our minds, because we're not talking about programming layer of abstraction or anything like that. This is just like things that happen inside your mind. But we need all this. And I'm using the word abstraction again and again. I'm talking about abstraction. What's an abstraction then? Well, we use this word especially in software because we very, very often refer to layers of abstraction. Or we say that we do not understand something because it's too abstract, or statements of the sort. And I want to clear some misconceptions before we go any further. Because what we do often in software is generalize things, make a thing more general. So someone might think that an abstraction is a generalization, and it's not true at all, and we're going to go explain a very specific example. And it has nothing to do with wrapping things up either. Again, think of a library where you have a lower level library, and you write another library on top of it. You try to abstract it. Abstraction has nothing to do with that. You might create an abstraction in the end, or it might not, but it's not fundamental to what an abstraction is. So with that in mind, I'm going to refer to what I call, because I cannot find another term for this sort of thing that I'm trying to define here, I'm going to talk about operative abstractions. So what are they? Well, they're fundamental abstractions that you need to keep in your head in order to understand a specific context, a specific thing in a specific context. But I'm not calling them fundamental, because there's nothing fundamental about them. You can always play with abstraction, change one, switch it to another. What's important about this is that they're context dependent, and if the context changes, your operative abstraction usually should change it as well. So these are, if we're talking about models that you create in order to understand something, we're discussing here what are the axioms that you put in the model. So this is where you need something to start from. But it's an abstract thing. Because all models are abstract. I was at some point having a discussion with a colleague, and he had a bug with some code, and the code was he was using some library. But the library, all that it did was a key value thing. So you put keys, you get values. But it was a key value thing backed by a single file. And the file contained all the keys and all the values. And I don't know, there was some sort of problem with the whole thing. And I remember him telling me, this library is so difficult to debug, and this is so abstract and it doesn't work. Why cannot I just have access to the concrete file? But that's quite interesting, because files are definitely not concrete things at all. Files are an illusion generated by the operating system for us, which in turn is made by other illusions, we have how do the APIs of the interface of disk drives and things like that. And files are so high level there, really. I mean, even with computers, back in the 60s, it took a while to invent files. There was a time without files at all. Nevertheless, nowadays, we think of files as very basic things, very building blocks. We understand them we think of them as a concrete thing, but of course, they're not a concrete thing. They're just one example of what I call an operative abstraction. To do this sort of thing, a lot of things in programming, you need files. So you keep files in your head, and you understand how files work, read, write them, things like that. But what you need to understand changes from context to context. If tomorrow I'm going to do something cloud-level programming, and all I'm dealing with is HTTP requests and things of that nature, and there's no notion of files at all, at least in the cloud. You can have local files, but to understand the cloud, you don't really need to understand files. You're thinking in terms of other things, as I said, HTTP calls, API calls, maybe not even HTTP calls. Maybe it matters that it's like an API thing, and the fact that it's HTTP is absolutely relevant. So tomorrow, I might need to change my operative abstraction to be able to think about the cloud in a different way without the baggage of what I knew yesterday. And that's why I don't call them fundamental, because there's nothing fundamental about them. It's just things which you might, if you consider them as concrete things, you might even call them tools, like tools for thinking, maybe, okay? But look, there's other things, like let's take, for example, mobile apps. Now, there definitely are files inside a mobile phone because it just runs Unix, but from the perspective of the user, there are no files on the phone, usually. They really try to limit your access to files. And if we're using abstractions just to understand the world, we should just accept any abstraction, for example. We should not be unhappy that we do not have access to a file system on the phone. But I know many people who are very unhappy that they don't have access to files on their phones. So why is that? Like, if abstraction is only something that we need to understand something else, it shouldn't matter the details of the abstraction, but we strongly feel that maybe some of us, we strongly feel that we need files on the phone. We like some abstraction we like more than others. So abstraction has to have some other sort of property for this to happen. And it's expressivity. We create models in our brains which are powered by abstraction, and we wish to say certain things or do certain things. But we are only using the abstractions that we are in our model. We created in our model. So we want to be able to express ourselves. So if you want to express yourself in a particular way and the abstraction doesn't allow for it, you're going to be frustrated. So there's this like human element, like we trained ourselves to think in a certain way. Like learning about the things, learning about the universe shapes your internal model of the universe in a certain way. That's then essential. Maybe it was essential at some point for understanding the universe, but nowadays, tomorrow, I just want to keep using the thing again and again, even though it might not be the right model. And we can obviously see this happening a lot with programming languages. Like all programming languages, almost all of them are Turing complete. Coincidentally, Q, the language I'm going to talk about, is not, but you know. But that doesn't seem to matter at all. People feel very strongly about using one language versus another. In fact, it's very unlikely, for example, for a Java programmer to start doing Python. I mean, it's possible for sure. It's far more likely, for example, for a Ruby programmer to start doing Python. So even in this sort of sense, we seem to understand as like a topology of things, and some things are farther away than other things, and some things are closer. But let's look at one possible reason for this. Why do we care about programming languages? A non-reason, I will call, is performance, because sometimes you have a performance problem. Let's say you're a Python programmer, and it's slow. So you need to make something quick, fast, performance code. So you cannot do it in pure Python. You do it in C or Rust or something like that. And it's fast, and it works, and it's great. You solve the problem. But I bet that most Python programmers would be unhappy. They would be unhappy that they had to use a different language. Like if given choice, if they weren't constrained by some other sort of thing, they wouldn't do it because they don't want to write another language. It seems that using tools, there's this expression. How do we choose a tool? Well, I choose, everybody says this, I choose the right tool for the right task. But it's obviously a lie because people consistently choose different tools for the same task. And they choose different tools and they do it consistently. So we choose tools that we like more or less than the right tool for the right job. And we hope that the tool is suitable for the job. So why? Because as we discovered previously, languages are tools for thought. They shape what we can think. They provide a way for us to think about things. But they also restrict us. I mean, it's not, you can always think about something else, but easy to think about things that are easily expressible, starting from operative abstractions, rather than things that are very far away. You don't want to like thread many needles to find something. You want a very simple explanation for everything. So languages are definitely tools of thought, and they're limited in what they can express. But it's also important for how we learn them. And there's, again, this engineering saying that all abstractions leak, which I really don't like, because it implies like this sort of metaphor that you have something and you create an abstraction around it, like a bucket, and there's holes in the bucket and something leaks. What leaks? Well, to understand why this statement is simply a category error, we have to look at types, and we will look at it. But I'm just going to say that we have to use the right abstraction for the right problem. So there's no such thing as leaky abstraction. I mean, we explained that in a moment, but I will show you an example. So when we invented computers, it was very difficult to operate them. All we had was essentially machine code or assembly language, and it was extraordinarily difficult to operate them. We spent most of our time in like the development cycle was so long. Like if you write some code today, maybe you have a result tomorrow, but more likely you have some sort of error tomorrow. So dealing with this sort of complexity, people naturally want to make their lives as easy as possible, as simple as possible. So how do they do that? By structuring things, by making things more and more structured, right? And eventually, I mean, we created higher-level programming language, for example, programming language that have if-else constructs and for loops and things like that. And they're much easier to use and much easier to understand. But we still had goto. We still had the goto statement. So you don't have to use if then else. You can just go to through all the programs. And that created spaghetti code. And again, very early in the history of computing, people realized that that's a very bad idea. In fact, this is a paper by Dijkstra, who, I guess if you just read the title, it sounds like they're trying to convince you not to use goto. And I suppose it's true in some sense. But this idea that we shouldn't use goto wasn't like something that was just prescribed out of nowhere, really. It came through an observation that in order to do effective programming, we looked at programs as they were being done. Some projects, some programs were successful, some less so, some cost more, some cost less. We looked at the evidence, tried to understand the differences, why in one case we could do one thing, why in another case we couldn't do the thing. And we saw that it's the more structured they are, they're better, they're cheaper, some other metric. And then we could formalize this, so it was essentially, before formalization, you had to be disciplined to take advantage of structure. But then we formalized it as a rule into the compiler, into the language. We made languages where we couldn't go outside the weeds. But I want to stress out that, first of all, structured programming with just if-else and for loops, is an abstraction. And it is definitely not a generalization, because I just told you couldn't write what you did before. It's a restriction, actually. And it's sort of like a generative abstraction in the sense that you could always structure your code in this way, but because you didn't have the guarantee that everyone will do this your colleagues or whatever, you couldn't really take advantage of it at maximum. So it generated essentially a new behavior, how people behave. But I want to stress that this was essentially a discovery. It wasn't, we didn't just, it was certainly not, we didn't wrap anything. We discovered that this is a useful property. We gave it a name. And when something has a name, it's much easier to refer and think about it. So it's a very different sort of abstraction than the one we talked today with like layers of complexity and things like that. So abstraction is really all about structure. It's about seeing the structure in something, deciding what's important and what's not important, and maybe formalizing it in one way or another. Or we come up with this sort of, you can even think them as equations, if you like, because they go both ways. To understand, we need to model. And to model, we need to abstract, because the real world contains like infinite detail. And we need to decide what is the useful detail and what's not the useful detail, and throw the irrelevant detail out. Abstracting means reducing the context to what's essential. We'll come back to this. And in fact, I think also, going back to Dijkstra said it best. Being abstract is something profoundly different from being vague. The purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. So, and I very much agree with this. So how does this bode with like the problem we see with layers of complexity and we don't understand the systems today? And there are definitely two schools of thought here. Like, on one hand, like the super high-level people with like monoids and end-of-functors, and let's make everything as abstract as possible, build this hierarchical type systems, and and there's other school of thought which says keep everything as concrete as possible, but we just discussed that nothing is really concrete, so what does that mean? So I don't have an answer, or I will not give you anyone anyway, but I will just say this, that please abstract, don't obstruct. Because a lot of the complexity that's prevalent today in the industry, libraries and again, layers of abstraction, really are designed to just hide things away from you, but in a way that do not provide any sort of useful abstraction. That's why I try to build another one on top, and another one on top, and another one on top. But really, unless we find the operative abstraction, nothing will really get fixed. So we talk about abstraction. We talk about how meaning requires abstraction, how understanding requires abstraction. But there's a very important thing missing in all the thing. It's types. Types. What are types? It's quite difficult to give a proper treatment of types, because types are essentially, types were invented at the beginning of the 20th century to solve different problems in mathematics. And there's a whole theory called type theory, which can formalize the entirety of mathematics. And does that have anything to do with either software or engineering or us as people? And actually, yes, it does. So I'm not going to explain the mathematical theory of it, of course. I'm here just to give you like an intuition, like how to think about things. Because you might be thinking of types because you use programming languages which have like strings, integers, different sort of record structures, whatever, maps, that sort of types. And those are types for sure, and yeah, there are sort of types you're going to see in Q actually. But I'm working with a more abstract definition of types. That one is types are particles of meaning. Now, what do I mean by that? Well, particles, you can think of like elementary particles, like electrons and protons and things like that, which you can abstract into a theory and generate the whole physical model from. Notice that, in case you didn't know, I said protons it was intentional, because it doesn't even have to be elementary particles. It doesn't even have to be fundamental particles. You can have particles made out of quarks or something like that. It doesn't matter. You can treat it abstractly if you want. So what do I mean by types are particles of meaning? Now, if I ask you, what is this? You're going to tell me it's a phone. Or if I could point to a bottle and ask you, what is this? You're going to say, oh, it's a bottle. Well, what you answer to that question, what is this, is actually a type. It's your understanding of the thing referring to a mental taxonomy of all things. And that's all what types really are. Now, in real life, you can have things included into other things, like, clothes are made of thread and things like that. So there's essentially a subtyping relationship between things. But it doesn't matter, because we have subtypes in computers as well, so it's perfectly fine, actually. Let me give you another example. Let's say you have an MP3 file with music, Beethoven's Fifth Symphony. You like the music. If I come to you and catenate dev random or something on top of your file, you're going to be very disappointed with me. First of all, if I really do that, you're not going to be able to play the file anymore. Because to play the file, the MP3 player needs to understand its type. And I just destroyed your file, so it cannot do that. So I did an operation that's essentially not type safe. But I can do something more subtle. I can take your file, open it in an audio program like Audacity or whatever, and destroy your file in a different way. I can put noise into it or whatever, but still keep it as a valid MP3 file. From your perspective, as someone who enjoys music, I've done the same thing because you care about the music. So from your perspective, the type of the thing is the music in it, basically. From the perspective of the MP3 player, its notion of a type is more approximate. It doesn't know what's in the type. It only knows the shape of the thing that you try to put in it. So we see that there are two notions of type here, which will become more clear. But there's an intrinsic one, which is the one inside the model. And then there's extrinsic one, the one that we want things to be, the one that things actually mean for us, which we exist outside the model. Again, if I go to your house and you have like a CD library, if anyone still has those, you're going to ask you, what is this? You're going to tell me, oh, this is Beethoven's Fifth Symphony. You're not going to tell me like this is a disc made from this process with grooves in it. What matters for you is its abstract quality that is meaningful to you. And when I ask you questions about what is something, what you're telling me is a type, always. Let's look at some example of calculus. This is a Lambda calculus. Lambda calculus was invented by Alonzo Church in the quest. It was just a tool. He was trying to disprove Gödel's incompleteness theorem, and he actually proved it correct, actually. But he invented this like formal calculus with symbols and things, and there are rules how to reduce things, what we can do with the things. It's just an exercise for the reader what this thing does, doesn't matter. But what really is, Lambda calculus is just programming with anonymous functions. That's all it is. So we have anonymous functions, we can pass them around, we can apply them, we can do things like that. We have a little bit more than that. We have arithmetic, and that's why I put a +1 and passed a 0 as an argument. We have arithmetic. You can augment untyped Lambda calculus to add more structure to it. But it's basically just a programming language. And it's like Python. I mean, I called it untyped. That's the term in the literature. I would call it unitype. It has a single type, the type of Lambda terms. But most programmers would call it dynamically typed. Like, it's exactly like Python. And we can put things like numbers and things in it. And just like in a dynamically typed language, if we run it, we can get into this sort of behavior where, we can get like an infinite loop, for example. Maybe we don't want that. Or simply the evaluator can get stuck. Like it expects to add two things, and we passed something that cannot be added together. It's like a type error, which is exactly like a dynamically typed language. So one might ask, okay, is there like a typed version of Lambda calculus? Of course it is, and it has a very useful properties. Specifically, it never gets stuck. The evaluation never gets stuck. And one example of typed Lambda calculus is Haskell, actually. Haskell is just, if anybody tells you that Haskell is complicated, just tell them that Haskell is just non-strict polymorphic Lambda calculus with type classes. That's all there is to it, really. So it cannot be complicated because it can be explained by very, very little rules. But look, we have a function that adds two numbers, right? And we know it's typed because it says int and int over there, right? But it seems kind of, don't you ask why the question, like even syntactically, you should see that on x and y, we haven't said anything about their type. We had to use a different line above, so they're disconnected even. And why are they disconnected? Because we invented type inference algorithms. A type inference algorithm just looks at your code, which doesn't refer to any type, and by analyzing the structure of the code, puts the types back in, basically. And this is quite interesting because it means that, hold on, like we need types to explain some sort of behavior, or we want types to guarantee certain properties, but we don't even have to write them. Where do the types come from then? Actually, this is a quite profound question, because if we do this to Lambda calculus, if we apply a type inference algorithm to our original structure and run it and do what I just said, we do a type version, we run it in a typed interpreter, it's the same expression, character by character. It's like untyped Lambda calculus and typed Lambda calculus behave differently because the typed one is more safe. But we didn't have to do anything to get here. Like we gained something out of nothing, it appears. But we did something. We analyzed the thing. We analyzed the thing in a specific way to be able to reject syntactically certain constructs over another. For example, and it's easy to understand a type inference algorithm. It's an integer there and it's a plus over there. Obviously, we can only add integers. So we assign an integer type to that function, and so on and so on. So it's we look at something. Oh yeah. We look at something, and just by analyzing it, we have two different interpretations of the same thing. So one way to think about it is that we have two completely different languages with two different completely rules about how to evaluate them and so on. But it doesn't, like, no, the fact that they use exactly the same syntax seems to be important. Another way to think about it is that we just took untyped Lambda calculus, we looked at it in a very particular way, we tried to give it meaning, and we try to give it meaning in a way that's important to us. Like we care that our programs don't get stuck, we care that they terminate. We try to apply our understanding of things like integers and addition and stuff like that on top of it, so we have this extrinsic notion of types that comes from our understanding, what we consider meaningful. And we try to see if we try to find those types like they were always hidden inside untyped Lambda calculus. To make this a little more concrete is like playing chess. Like chess is there's syntax, like there's pieces on a board, and there's rules. Pieces can only move in a specific direction, and so on and so on and so on. But I'm sure that nobody plays chess just to play with the rules, how the chess pieces move. It has a meaning to us. We like playing chess, and it has a deeper meaning to us. That's not evident in the rules that just describe how the chess pieces move on the table. So what we really happen is that we try to understand something, we find types hidden within. So when we try to relate our understanding of anything, when we try to relate meanings, and types are meanings, I'm going to say that again and again, we find, or we can ascribe types to the thing inside the model. So type are very powerful, and I won't go very deep into it, but type relates syntax and semantics, because type can say something about the representation domain. But more importantly, what's important for us in Q is that type relate extrinsic and intrinsic meaning. Intrinsic meaning are just the judgment that you put inside your model. Like this, it has to be this way. And it's essentially an axiom by definition. And those are really our types. Those are types that I call the particles of meaning. Those are the intrinsic meanings. Extrinsic meanings is like whatever we want, really. But we're trying to create a model for something that we want or we want to understand. But once we figure out that the model, the process of modeling is typed, that means that that operation that we're doing means relating the extrinsic and intrinsic meanings. So we saw this before, but we know it has to involve types as well. So what do types do? Types provide a way to make sure that the model we're trying to create actually is relevant. We're not just trying to create an arbitrary thing, but it's actually relevant to the problem at hand. And types provide that. There's the only way that this thing is provided, actually. And type safety is just an additional property that means meaning preserving. When we say that something is type safe, we mean that in the representation domain, whatever we do with it, whatever we play with it, we do not break its meaning outside. We preserve the meaning whatever we do. For a static type system, then we can do that statically, but type safety in general, that's what it means, that we can play with things inside the model, inside the representation domain, and we can be sure that it's still meaningful outside. Now, I promised you this has something to do with the cloud. So, what is the problem with the cloud? Well, there's this joke running around that the cloud is just someone else's computer. And to me, this joke is amusing on several levels. On one hand, it's actually true. It is just a bunch of computers owned by someone else. But there's a more figurative sense to it. Because the cloud works kind of like a computer, in the sense that and it kind of replaced computers, literally even, because instead of having a computer, as having a server room managed by ourselves, we can just use the cloud. And it feels like a computer to me. Like the things that I used to do on my computers, now I do on the cloud. And I don't consider the cloud to be like a bunch of virtual machines, but I consider the cloud to be like an API. So I interact with the cloud through this interface that they're telling me, which is just another interface, like how would you interact with the computer? But the cloud, the notion of a cloud as a computer has some limitations. Like it's like we're back in the 60s again. Like again, we lost all interactivity. All that we can do with computers is schedule essentially batch jobs. The development cycles have grown again. Like it has to go through the CI pipeline. You have to generate Docker containers. You have to do this. And again, once you errors out, because of all this chain, the error you get out probably has nothing to do with the problem you're trying to solve. And the tooling is very, first of all, it's very proprietary, which is just like it was in the 60s. All computer manufacturers had their own tooling and had their own operating system. Like AWS is different than Azure, for example. And also like in the 60s, people trying to build abstractions that kind of meld these differences away with some level of success. But the tooling is so difficult to use, and it's so abstruse, and I intentionally use the word abstruse there because it relates to, it's difficult to understand because we do not have like the proper mental model to understand the tooling. It operates at the wrong level of abstraction. So you might be thinking, okay, am I saying that the cloud is difficult because we're in the 60s? No, that's not what I'm saying. Some people are saying this, but I'm saying something far more specific than this. The problem with the cloud is that, as I said, we only interact with it through APIs. And what do those APIs do? And we pass usually YAML, sometimes other formats of data back and forth to the cloud. What you're doing to the computer by trying to pass like new configuration into it, you're changing the state of the computer, of the cloud, in a way that will affect its future behavior. So it's not a black box, just like computers are not a black box. By programming the thing, you change its behavior. Programming the thing, programming languages. But we're not using programming languages to configure or to affect behavior, how we want the cloud to behave. We pass data. It's definitely data. And usually it's in a YAML format. But whatever it is, it affects the cloud and how it behaves and how it will behave in the future in a way that resembles the way we program computers even. And in normal day-to-day life, I mean, from a strictly mathematical point of view, we can never separate data and code, but we can pretend to pretty well. And usually in day-to-day life, we do not have to worry about things like that. We can keep data and code separate. But we cannot do the same thing with the cloud. This notion interacts fundamentally. Therefore, what we do with the cloud is program it. All the data passed back and forth is a program. And by the way, I'm not talking about like static configuration. I just say like, oh, we need 50 virtual machines or something like that. No, I mean like in APIs, parameters passed in APIs, any sort of data passed into APIs, as long as it as long as it has side effects, we're really passing programs around. But the programs passed around are not written in any particular programming language. They form ad hoc domain-specific languages that are specific both to the technology itself, say Kubernetes, but also specific to like the business problem. You try to solve a particular problem and you invented this one microservice. And each microservice uses a different notion of its own internal DSL. But we don't even realize that we're dealing with languages and programming and things. And we don't have a way to understand them. Like, that's the problem with them, because we're not even thinking of them as being languages. They certainly don't have, like, clear language-level semantics. And it's very difficult to understand them as pure code, because they're not pure code. But it's actually even worse. Not only they don't have semantics, they don't even have syntax at all, because all of them are essentially encoded into YAML. And the thing about encodings is that, as I said in the beginning, the representation has to have some useful properties for solving the task. For example, Roman numerals and Arabic numerals denote the same concept, but it's very difficult to do arithmetic with Roman numerals. That's why we got rid of them. And it's just a problem of syntax. They mean the same thing, but the syntax does matter. And all we have is YAML. So over the past 60 years or so, we try to advance the field of programming languages and engineering and how we think about things, and we invented a bunch of stuff that help us shape our thoughts and change the way we think about things. And I'm not, by the way, some of these things are good, some are, less good. I'm not going to tell which one I don't think they're any good. Some of them I think are really bad, but it doesn't matter. It's part of our culture and part of our shared understanding, and we think of engineering in these sort of terms, and of course, you can make 10 slides like this, because in 60 years we had lots of evolution and lots of progress. But for embedded DSLs inside API calls, none of this applies. Absolutely none of it. So our understanding, the way we think now about computing and about languages, doesn't meld well at all with the DSLs embedded in API calls. So that basically means not only we've thrown away factual advancements that make your life easy today, but we simply lack a way to think about about the DSLs. Essentially, the problem, I think, is that because languages are tools for thought, we simply cannot think about anymore. We cannot think about embedded DSLs anymore because we don't have the tools to think about them. So we need a way to fix this problem. It means that we need semantics for these languages. And all starts from the fact that what we do with the cloud has to be meaningful, because otherwise we wouldn't do it at all. So presumably there's a reason for things. We just have to find the reason. Once we understand the reason, we can start to look at its structure. How? Which means we have to discover the abstractions that are inherent in its structure. And of course, we need types. Now, how do we solve this problem? Well, we need some sort of tool or some sort of framework of mind or something that has to have the modeling power to model all these embedded DSLs. Now, unfortunately, the usual languages and tools that we have are inadequate for reasons that's already explained. And people have tried to build like higher level abstraction on top of Kubernetes and things, but they never got like the satisfying answer. So we need powerful modeling capabilities, but with different sort of things that the usual languages. We also want, ideally, something that engineers understand, because all of this is just cost. Like, we're trying to solve business problems, but we have to deal with this cloud complexity. And for example, we already have modeling tools that are based on dependent type theory. For example, Agda, Lean. There was a talk about TLA Plus here yesterday. But these tools, as powerful as they are, engineers don't know them, and they're quite difficult to understand. And I think people should try to understand these tools and this way of thinking more. Nevertheless, as I said, we're dealing with a cost problem. We have to fix something. It's a very tough sell to explain to engineers, oh, yeah, you need to learn Agda, by the way, too, and then it will be better eventually. So ideally, we would like to some sort of solution where engineers don't have to learn anything at all. And also, even if you know Agda, the cloud is defined in terms of YAML and JSON and other formats and open API and stuff like that. You would just have to do busy work of encoding that sort of truth into Agda for no reason at all. So no, we just want some sort of tool that natively understands your source of truth as you defined it already, and it doesn't need any sort of impedance matching or anything like that. So I will give you a taste of Q. Q is a very simple language, but of course I won't go through all features. I will only go through the features that I think are relevant to why do I think it's a good solution for this sort of thing. So here is hello world in Q. What I say there is that I declare hi to be hello world. And I'm going to stress the word declare. I said declare, not assign, not define, but declare. What does declare mean? It means, well, it just means that we declare something. And it's not assignment specifically, and we will see in a moment. Now, in Q, you can have comments, which is something that some languages using the cloud today don't have. So that's an improvement. And you can refer to things previously declared, and you can run functions of them, for example. And in this case, of course, we expect two upper functions to make the thing uppercase, and we can compute its length. By the way, what you see on the left is Q, of course. What you see on the right in this case now is also Q, but Q has native integration with all the cloud languages like JSON, YAML, but also other like a JSON schema, and understands other things. It understands Go directly, for example. And it's a first-class thing in Go to be able to interoperate this source of data from any format you want into any format you want. This is JSON. It can also output YAML, for example, because that's what you probably want. Q has arithmetic. It has arbitrary precision arithmetic, which is very useful for doing things like financial calculations and things like that. It just uses the Go standard library package for that. But all these declarations that you see on the page, I put them in this order for ease of understanding, but the order is irrelevant. So the order doesn't matter. You only have to have the import on top. So what do we do with these values? Like, we need to package them into some more interesting structures. Here's a list, for example. It's a list of 8 elements, I think. Yeah, 8. Lists are, maybe list is not the best word that we should use for this, but that's what we have. It's basically like a tuple, so you have to know the elements beforehand. It's not like a list that can grow. In fact, everything here is immutable. Nothing can change ever. And lists, of course, if we try to output the lists as JSON, we get this sort of structure. But YAML, we get this other sort of structure. We have lists. Do we have a way to package data into like basically group data together? Currently, we call this a struct. We might change the name because it usually structs in another language denotes some other sort of thing. But they are a way of grouping related things together. In fact, what you have inside the curly braces is a relation between all those 3 things. Another interesting point is like population. You see that we have a number of suffixes. And we can declare things you have strings, all the data types that you would kind of expect. And once we have declared something, we can use it. We can put it inside other lists. We can create bigger things out of smaller things. I mean, of course, you expect that out of any language. And we can print what we just did in YAML. And this begs the question, how is this different in YAML? Because everything that we saw before, so far, were things that you could do in YAML. And that's a very good question. But coming back to the declaration thing, we do not have to declare concrete values, the type of things that you would put in YAML. What you actually declare for every object is a set. You can say that x is an int. You can say that s is a string. You can think of an int like a set that contains all the integers. What we did previously, we were just declaring that it's a one-element set with a concrete value in it. But here, this kind of looks like a type declaration that you would see in some languages. But there's no difference between types and values, really. We're doing the same sort of declaration. We're declaring that things are this. We're declaring properties of things. We're declaring that x, you should read this thing as like, there exists an x that is an int, or there exists an s that is a string. I haven't told you which one it is, and I might tell you in the next slide. No, before the next slide. Before this, we can also say things that are more interesting than just being an int or a string. We can say that IP is an IPv4. Now, what's an IPv4? Well, if we try to do this sort of thing, I said that x is an int, then I also said that x is 100. Fine, no problem there. What about IP? What I said about IP, it looks like a string, though. It doesn't look like whatever a net IPv4 is. It has to have the string representation over there. But no, I really mean it's an IP because, for example, if I put the wrong thing in there, that's something that's not an IPv4, it will complain to me precisely why it's not an IPv4. How does it know that? Well, that requires some quite further explanation, which I will not go into. But what I want to stress is simply the fact that we declare what properties we want things to have. So, and we can declare any number of properties. It's not like we can declare, okay, it's a type, it's a value. No. We can refine things as much as we can, as much as we want, but we can only make them smaller. So in the first case, you can think of int as being like all the numbers, an infinite set. But we can say also, by the way, x has to be less than 10. So we take only the numbers less than 10. But it's also, you can think of less than 10 as being like an anonymous type, isn't it? And once we try to put the 5 into it, again, it works because it's both an int and less than 10. But like before, if we try to put something that's incompatible, it will complain. So the way to think about this thing is that it's like a database of information, and it accepts any sort of information that's compatible with its view of the universe, and it can only refine itself further and further until it finds like a contradiction, in which case it has to error out. If it doesn't find a contradiction, it just lets you refine things further and further. But if you look at the thing, by the way, is that the first one, x colon int, is kind of like an organization-wide schema. Then someone might decide that, oh, you know, for this particular group, we want x to be less than 10, which is kind of like policy. And then somewhere in the configuration, something says that x actually has to be 12. So we get all this, we get policy for free, essentially. We don't have to think, we don't have to design the program. Oh, it has to accept sources of truth from like different groups, and they have to relate in a certain way. No, it's all implied in by the language. And you can decide as a user of the program if you want to structure your deployment that way to have like a separate group for policy, which, yeah, and it all works for free. So declarations can only be more and more specific if you want to gain more information. Again, you can give names to things. So range now are all the integers between 0 and 10. But look, something funny happened. In the Q output, it simplified itself. It says that it knew that int, which is greater than 0, is an unsigned int, and it said that to us. But it also said, okay, it's an unsigned int, and I will stress the word and, it's less than 10. because all the declarations it's an implied conjunction. It's and, it's range colon int, and range colon n, and so on, so on, so on. So all of them are ANDed together. And of course, we can do that explicitly. If we want a city, and we know, let's say we know sources of truth about the city, sources of information, what the city we want to behave like it has a name and population. But also, I might think, oh yeah, you know, it might have an elevation. And if I say an and there, I mean, the way we compute it is like this. It's like the struct, it gains a new member, basically. Because this new struct is more specific than the previous one. It has more information. And it has more information, it becomes more and more specific. And it also works pointwise. Like if Vienna, I claim that Vienna is a city, I define city above, I claim that it's a city. Oh, and by the way, it also has a mayor. I didn't say anything about mayors in the city declarations, but it's no problem because it's just a more specific instance of a city. It can have more properties. We know we can have it know its mayor, but we don't necessarily have to know everything about it because elevation, I said it's a number, but I don't know the elevation of Vienna. I know it's between that range and that range, and it's fine because that range is like a finite set of numbers versus like the infinite set that we had before. We restricted it further, but it's fine. We haven't found a concrete value yet, but it's all right if we don't need it. So, and if you do it for lists, it works pointwise. I won't go into that, but I will go into disjunctions just a little bit. So if conjunctions are and, disjunctions are obviously or. So if you look at inverted range over there, you see it's basically we carved, so we took all the numbers and we only keep the ones that are less than 10 or the ones that are greater than 10. So we carved out something in the middle. And you can think of this as set union. It's exactly like set union. You can take this thing and you union it with this other thing. And you can use it. Disjunctions are a source of complexity for Q, and I won't go very much into it, but they're very, very useful because they are used to model optionality, or they are used to model things like when you have disjoint things, but you need to treat them together in one way or another. For example, only a company might have a tax ID, but both a company and a person have a name. So what we say there by legal person, I just say that it's a person or a company, and it's just set union. We say it's this thing plus this other thing. And we have another example how we might use it. And again, I don't think I have an example here, but if you try to do it, it will really complain to you if you try to instantiate it in a wrong way. And all these properties, the and or, are very well behaved mathematically because we want Q to be compositional. By the way, having this associativity, commutativity, idempotency, plus another couple of properties means it's a mathematical lattice, but it doesn't really matter for using Q. But the effect of it for using Q is that you don't have to worry about order, about where information comes from. It all works together in the way that you expect, and it's very well behaved in this sense. Basically, it's compositional. We saw function application, but let's look at a more interesting example. If you want to see the release date of this album, it kind of looks like a string, and we don't like that because, as I said, types are meanings, and that has to be a date, so it cannot be a string. So what type is it then? Well, we can model this with functions easily. We know that it has to be a string because we express it, we wish to express it that way, but it also has to conform to some specific format. So now if we try to put the wrong thing in there, it will complain to us. Hash album is well, we call it a definition, but the names don't really matter. But what you see, the last line there is like an album is an instance of hash album. Therefore, it has to conform to this. Otherwise, it will complain. And the date in time format is just the Go date format, by the way. Comprehensions. Comprehensions are a way of doing some sort of limited computation within Q. That's one way to think about it. Basically, we can iterate over elements. I prefer a more abstract way of thinking about it. There's a way of modifying the shape of things. For example, in this thing, we took strings from a list and made a struct with the keys of the struct as being the strings from the list. So we can play with the shape of objects. We can go from one shape to another shape, essentially. If we have two lists, we can do like this is a 4 inside another 4, but we're really doing their matrix multiplication. Of course, when we iterate, we can put additional selections, like we only take like the positive numbers over there and calculate their sum. So we also have if there. We can do completely wacky things, like we can, in here, we invert the keys and the values of fruits. And also, for the values, we double them. Why would you do this? I don't know. It's just an example to show you that you can really have the power to use the shape of an object as an input to some sort of computation, which allows you essentially to generate types. And Q is all about types, and types are meaning, so it allows you to create exactly the types that you want using essentially computations. Now, that's all I'm going to talk about Q in this particular talk. There's way more things to talk about, but I think this is like the important things for the problem with the cloud. With templating, there's a way to generate data, and you can think of this like generating your Kubernetes config from some template, for example, in a type-safe way. Closed values are, again, very important. We saw that we can add to a struct fields, but we can restrict that if we want. So there's more to it, and especially there's a lot more in the tooling layer and in the API layer. We have put a lot of effort into making things usable in the cloud context. So it's essentially cloud ready. As I said, we natively speak JSON and YAML and a couple of others, and we just want to add more and more adapters to make it to be completely like a polyglot thing and speak every language out there. But I'm not going to talk about that. We're just going to look at it again, like have we actually solved the cloud solution, and what did we have available? Because we wanted to engineers, we wanted to provide some sort of solution where engineers don't have to learn much. So I look at this as this way. What do engineers understand? And I talk about sets a little bit, set intersection and set union. These are concepts that engineers understand, so that's good. They also understand the notion of logic. They think they do, but because sometimes you're going to hear programmers say things like, oh, all programming languages are the same, it's just different syntax, but it's all logic. And it's actually not quite true, which I guess this talk was exactly the way it's not true, but there's a grain of truth to it. So engineers know some sort of logic. They know propositional logic, which deals with like conjunctions, and or and things like that. So we can make judgments. We can make we can think of things in the way like if it's raining, then it's cloudy. Today is raining, therefore it's cloudy. They understand this sort of thing, but they understand more than that. They understand like quantifiers, like predicates are like properties of things. So I can make a universal quantification by saying all CraftCon participants are alive, or I can make an existential quantification. I say that there are some CraftCon participants who are speakers, and who are speakers is a predicate that applies to participants. They can be speakers or they cannot be speakers. And to understand this, is just reading comprehension, which we have to do as engineers because we read documentation and we have to understand things in that context. So that's good. We have logic, we have set theory. But really, these things are things used in Q, so it means that everybody understands Q at the semantic level. Engineers also know about APIs. I mean, they deal with the cloud every day. They understand how to use command line tools, and they understand how to use APIs and tools in data transformation pipelines, which are essential to their everyday work. So they know how to think in those terms, not just do them. And of course, they know various languages. But more important for us, they know JSON. And I think I forgot to say, Q is a strict superset of JSON. So if you know JSON, you can already start using Q. So it means that engineers already know how to apply Q in their day-to-day life, And they also know syntactically how Q works because it's a very simple extension and pretty obvious extension over JSON. So Q can express what engineers understand, and we think that it does so with the syntax they accept and they already understand. So we wanted this, we wanted powerful modeling capabilities and set theory and first order logic and model most things, including even most of mathematics. So we're good there. I think that we have something that engineers understand. They understand the logic of Q. They know the syntax of Q at least to some level. And as I said, Q is all about being cloud ready or cloud native. We speak all the other languages. We're adding more and more. And we just want to be like a native cloud citizen. So I think we have what we need to solve the problem. Some parting thoughts about the Q community. Of course, if you want to learn more, we have our website with all of the documentation and stuff like that. We are currently revamping our website. There's another third-party website called tutorials.com, which was written by a third-party member, and we are very grateful for that. And we're actually quite proud of our community that we have such a vibrant community that produces such high-quality materials. So yeah, we have a Slack. You can join us on GitHub. We have frequent community calls. Yeah, that's it. Thank you very much.
Thank you so much, man. That was very enlightening. Honestly speaking, I had a little bit of coding and development classes when I was in university, and one of my biggest problems back then was, all right, but who created this language? Who made this language a language? You know, and how does computers understand this? Like, this is referring to the beginning of your presentation, right? So what is a computer and how, what are programming languages and etc. The second part of your presentation, I'm sorry, but that got a little bit too technical for me and I got lost a little bit. But I'm sure that it was very enlightening for everybody. I want to ask if we have any questions from Slido. We don't have any questions from Slido. From the audience, oh yeah. Yep.
Hello, my name is Daniel.
Hi.
My question is, could you elaborate on the differences between languages like Agda and Idris?
Yes.
And in what cases would you use them and when would you use Q? Thank you.
Yes. It actually comes, I mean, yes, I kind of sort of lied to you a little bit by telling you that Q is all about types. I was telling you the truth that types is about meanings, but Q cannot really encode types. It can encode sets. That's why you have this distinction that things can include, and you have subtyping. You can include things into other things. So, which is useful for many things, like if you have a taxonomy of objects that's maybe vaguely defined or like the boundaries are not clear. Q is great for that because you can express this subtyping natively. Whereas with Agda, an object can have a single type. There's no subtyping. And you have to encode this collection, an object that can be part of many collections by yourself, which is, of course, possible to do in Agda as well. So come back to your question. I guess it's in principle, Agda can model everything. It can model much more than Q can, but it's simply much more difficult to use. That's I guess the main argument for Q is that we cannot do things to the precision that Agda can, and we cannot use Q as a theorem prover, for example, because it's using classical logic. It doesn't use constructive logic. But we think that it's easy. It's something easy for engineers to understand, and it's just easy to get into as opposed to Agda. I mean, I think everybody should learn more Agda, but yeah.
Thank you very much. Any other questions? We have potential 3 more questions. Not really. Okay, Aram, thank you so much for coming.
Thank you.
Yeah, you have another question. Okay, beautiful.
So you mentioned that there were developed some software engineering practices that you do not really like. Could you elaborate on them?
Not publicly.
Okay.
That's a talk for together with a beer. All right, everyone. For everybody that is watching online, thank you so much for being here with us and watching the talk of Aram.